Welcome to this webinar delivered by Stork. My name is Savannah Hance, consultant with Stork Asset Management Technology, and I'll be your moderator for this webinar. Thank you for taking the time to dial in. We live in interesting times, making us all reevaluate choices that we make in our daily lives, so all the more thanks for choosing to join this call. From our side, we're happy to share our knowledge with you, and hopefully it can help you navigate the current crisis situation. Of course, due to this crisis, many of us are working from home, so hence the less than business background that you may see behind some of the speakers. The duration of this webinar is half an hour. To avoid static background noises, we've switched all of the microphones off, but we really greatly do appreciate your questions. So if you have questions, please enter them during the presentation via the Q&A button at the bottom of your screen, and we will try to address them at the end of the presentation. The subject for today is periodic inspection, continuous condition monitoring, or APM 4.0. That is the question. Selecting the right asset reliability strategy may be the question that keeps many of our customers up at night. Currently, at conferences, on social media, and in marketing communications, a lot of focus and attention is on the newest technologies like machine learning, predictive analysis, and anomaly detection. And it seems like this would be the only valid strategy. But is that really the case? Is there a one-size-fits-all approach with regard to an asset reliability strategy? In some cases, sure, this might be the best approach. But in many cases, the business case of this strategy just isn't proven and achievable. So I'd now like to introduce Johan Furkett to share more about this and to help you navigate between the hype and the reality as you make your decisions. Johan is a consultancy manager with Stork and a certified reliability leader for different asset and maintenance management projects in multiple asset-intensive industries. I wish you an inspiring and educational half hour. Johan, the floor is yours.
Thank you for your introduction. Basically, there are three main categories of strategies to be used or could be implemented in your company. It could either be run to failure, time-based maintenance, or condition-based maintenance. Is a proactive strategy like condition-based maintenance the most feasible and effective option? If not, maybe alternatively, the asset may run to failure or time-based preventive maintenance is applicable. Is one strategy better than the other? Maybe. This seminar will provide you a clear answer to that question, including some real customer cases. Now, before I start with my presentation, just a few words on asset performance. Improving asset performance is not something only the maintenance departments should take care of. It's not the focus area of only the maintenance department. It is as much as the focus of operations. Operations has as much influence on asset performance as maintenance does. So to make it happen, to make asset performance management work in your company, make sure that you eliminate all the organizational silos and enhance a cooperation between maintenance, operations, and engineering. So before we start looking at the different condition monitoring techniques, what problem are we trying to solve? We do that by looking at the most dominant failure patterns. First, we can have what we call infant mortality. The failure happens especially at the start of an operation after the equipment was installed or commissioned or after a repair. The other one, quite opposite, is that you have relatively low amount of failures, and by the lifetime of the equipment you see some kind of wear out, and at the end of the wear out zone, at the end of the lifetime, which we call the wear out zone, you have more probability of failure. The third option is random failures. Failures that happen over the lifetime of the equipment. They happen. Sometimes we don't know why. It could be that we operate outside of the operating window, that the quality of the raw material has changed, that we have process inputs that have changed, or that we have maybe changing weather conditions. The failures happen, and in some cases, we just don't know why. Before I continue with my presentation, I would like to invite the audience today to participate in a poll. So please get ready to select one option out of the 6 on the screen. What do you think? What is the most dominant failure pattern? Is it A, wear out, meaning slowly increasing probability of failure, and when the end of the lifetime you see more probability of failure in the wear out zone? Is it B, infant mortality in the beginning, slowly increasing probability of failure, and again at the end of the lifetime in the wear out zone, increasing probability of failure? Or is it C, fatigue, slowly increasing probability of failure towards the end, but we cannot notice one wear out zone at the end, not clear wear out zone at the end? Or is it option D, infant mortality, high probability of failure, and then constantly a probability of failure towards the end of the life? Or do you think it's pattern E? Once the equipment is new installed or after have been repaired in the workshop, you see less probability of failure. You see less failures appearing. But then when in the initial break-in period, you see a slowly progressing pattern of failures. Or is it pattern F, random failures? And so you have a constant failure pattern at all ages of the lifetime of the equipment. So as you will see at your screen, you have some different options, 6 options, and you have to choose one of them. So I give you some moments to pick your pattern that is, in your opinion, the most dominant one. So Laura, can you please show me the results of the poll, please? Oh, thank you. This is very surprisingly, and it also confirms what I see a lot when I do these kind of workshops and ask the same question to many of our customers. We see that the most of the dominant failure pattern that the audience has chosen has bad-up curve and fatigue. Many of the people think that the bad-up curve and fatigue are the most dominant failure patterns. But in reality, based on researchers like Nolan and Heap in the 70s and John Mowbray, the RCM2 practitioner, and I have his book, which I often use, is that 68% of infant mortality is the most dominant failure pattern, and 14% followed by 14% random failures. What lesson can we learn from this? Infant mortality means that there's a high probability of failure when we install and commission a new equipment or repair an equipment, and that we put that back into operation after a maintenance intervention. So what does that mean? What does that mean is that the state or the condition of the asset after a repair, after installing a new equipment, is worse. And that's why we use often the synonym for infant mortality as worse new, worse repaired, meaning that it is very important to also take care of the work execution management. So when doing a maintenance intervention, the quality of the repair has a large influence on the failure patterns. So make sure that when you engage with an EPC contractor or an operations and maintenance contractor, that they provide you with the right quality of work. Because it can happen that when you interrupt a perfectly running turbine to do a preventive maintenance work on it, that the performance of that turbine is worse than it was before. So please bear in mind when looking at failure patterns that infant mortality is the most dominant one. The other conclusion is that only 11% of the failures are age-related and 89% of failures are non-age related. So the vast majority of the failure patterns could be subject to condition-based maintenance. As condition-based maintenance, one of the key characteristics is that it improves the accuracy of the probability of failure. In short, condition-based maintenance helps you to better predict when a maintenance intervention is needed. It reduces the unplanned downtime of your plant, and also it reduces unnecessary tasks that you have been doing by just doing time-based preventive maintenance. In this period of COVID-19 pandemic, better scheduling a maintenance intervention also might lead to less people on site, which is an additional benefit of condition-based maintenance. What are the three flavors? Well, within condition-based maintenance, we see predominantly periodic inspection, continuous condition monitoring, and predictive maintenance, or as we call it, APM 4.0, with reference to the Industry 4.0 era we are currently in. Before I go more in detail about these different techniques, I want to take a closer look at potential failures. A potential failure is a condition that we can identify and which indicates that a functional failure is either about to occur or in the process of occurring. For a long time, we have looked at defining a failure in this way. The equipment breaks and we will fix it. This was for a long time the most dominant maintenance strategy. The graph on this slide, where you have the vertical axis for looking at condition over the horizontal axis looking at time, the graph shows the condition of an asset and how this asset condition degrades over time. This graph we call the PF curve. The time from the potential failure point P, the point where the equipment starts degrading, to the point where it actually fails, is what we call the PF interval. It is also called the warning period, the lead time to a failure. And this is what we call the current today's definition of a failure. In the red zone, as you can see on the screen, the degradation really can be noticed. And in that period of time, in that zone, the equipment is no longer performing its function as intended. The main objective is to capture a potential failure before it actually occurs before point F. So the key challenge is how can we move left on the PF curve and have more lead time to properly schedule a maintenance intervention before point F, or maybe even before point P. So, but actually we don't know where point P is. It can be here. The degradation could be started over here or here. We don't know. Now, if we detect it over here, we are pretty late in the ball game. Is there a very short lead time to schedule a maintenance intervention? To give us more comfort, we need to find ways to create extra lead time, or even based on certain criteria. It's a very complex equipment. It's high critical, and we need more time to plan properly a maintenance intervention, or order spare parts which are very capital intensive. We need a longer lead time. Now, as I promised, let's take a look at the different techniques. We have periodic inspections as the first one. Here we enter quite late in the interval. This is the main characteristics, is that it usually be executed by people on site who walk down the plant and do a visual inspection, use their human senses, use a infrared camera to do an inspection, take an oil sample to do an oil analysis. Key elements of this, of course, is that we try to have an inspection interval which is shorter than the PF interval. For instance, what we have seen in practice, for instance, if your PF interval is 8 months, start maybe with an inspection interval of 1 month. Then you're looking at the safe side, but at least that you know that maybe you can extend it to 2 months. The advantage is it's rather low cost. People are already on site. It's very precise. It's very flexible. But the downturn is that it's rather late in the process, and it depends largely on the experience of the observer and the state of mind of the observer. If you want to create more lead time, let's take a look at the second option, which is condition monitoring. It's designed to detect failures effects such as changes in vibration, in pressure, in temperature. It uses technology. It uses technological observation methods to collect data regarding the actual condition and health of the equipment at this moment in time. When a certain parameter goes beyond an unacceptable level, a maintenance job is scheduled and executed. Actually, at that moment, your asset is really telling that it needs maintenance. And together, what we do with our customers is to find what are the right sensors to capture the failure data. We install it. We need to define the ways to transmit this data. We store the data. We define the thresholds, the bandwidth in which the parameters should operate, and we monitor the equipment. And this can be 24/7. For some reasons, as I mentioned before, we need to detect the failure much earlier in the PF curve. We need, in this case, more data from different data sources. As this large volume of data should be analyzed to predict more accurately when the failure will occur and when the maintenance intervention should be scheduled, the large volume of data, this cannot be handled by humans. We also look in this case on data that's residing in images, in other devices, in text, because maybe that data resides in digital content. Let's make this a little bit more practical. We have a pump where we installed sensors, but this pump operates in a very complex environment. is part of a complex process. We had some issues with that pump, which causes unplanned downtime. Therefore, we took the decision to use as much as data from different data sources to make a better prediction when we have to do maintenance on that pump. We look at process data, we look at sensors data, we look at work orders data, data that's residing in work orders. Based on the existing data, we label the patterns in that data as good, as a good pattern, or as a bad pattern. So we say, in this pattern, the equipment is behaving as normal, and in another pattern, the behavior of that equipment is abnormal. After labeling of the patterns, good or bad, we select the right algorithm and develop a model that describes the pattern. Of course, this model is not ready to be implemented. We need subject matter experts, which we have within Stork, spread it around the world to use their expertise to train the model and to make that model more, to increase the level of confidence of that model and to be able to define more accurately when the failure will occur. Using data analytics tools, machine learning, we can identify normal and failure patterns. We can even go a step further by using prescriptive responses, not only to define when the maintenance intervention will have to be scheduled, but also which action we should take. We use dashboards not only like for condition monitoring to see at the current health and condition of the assets, but also to predict when the maintenance intervention is needed. What is the best stepped approach to define the best condition-based maintenance strategy for your company? Obviously, we determine based on criticality analysis which assets we are going to focus on. We define the different disciplines and per discipline the type. For instance, we have disciplines like rotating electrical instrumentation equipment, and in rotating you have a gearbox or a pump or a turbine. So based on our experience within Stork, we want to select with you the right solution, and we do that based on a questionnaire. The first question we ask to you is what problem you are going to solve. What is the business case behind it? What asset objectives you want to achieve? Because condition monitoring and predictive maintenance are quite costly to implement. So there should be a clear ROI, return on investment, and a clear saying, okay, we have this problem we are trying to solve. Then secondly, we look at what is the quality of your data and the availability of your data. And then thirdly, we look at the complexity of the equipment. What external influence factors we have on that equipment. The outcome of that questionnaire is what is the best monitoring solution for your equipment. So to summarize, before I have some slides on references and use cases, define your objectives. Look at the operating context. So which industry are you in? Look at the equipment type. Is it a pump, a turbine, or is it static equipment? In which ways can it fail? So what are the failure modes? What strategy you want to apply, and which health indicators we are going to use, which sensors, temperature, pressure, leaks, but also which digital content we need to be analyzed and used for information purposes. So currently we are implementing these monitoring solutions in a lot of industries and a lot of customers. We see that within our customers, we implement all of three, not one, but all three, next to run to failure and time-based preventive maintenance. By doing that, we also see that our customers consider Stork now as a proactive service provider. We also see with digital transformation, which we are assisting our customers in looking at our maintenance service contracts, we are more considered now as a proactive service provider, using data and our experience to help our customers to improve their asset performance. One customer challenged us with the furnaces we are doing maintenance on. They say, yeah, proof that it works. We looked at the different data sources. We look at the maintenance history of our people which reside in different systems. We grouped the sensors. And afterwards, we looked at the failure patterns, what good looks like and what bad looks like. We developed the algorithms, trained the model based on the experience of our people on site. The outcome was that we could prove to the customer that we could postpone 3 cleaning activities per year. We can avoid 2 days of shutdowns per year per furnace, and we can reduce the maintenance costs with 3 million. And there we see that the collaboration between the customer changes over client-supplier towards more a partnership. So if you do it well, there's a clear value to achieve. Your workforce will be more productive, work safely, and especially in this COVID time, this is very important to have less people on site. By reducing unplanned downtime, you increase the availability. By better preparation your work, you see a reduction in inventory of your spare parts. But last but not least, also you can extend the lifetime of your equipment. As you have heard in the last minutes, all strategies have their place as long as you take a stepped approach to define the right strategy, whether it's run to failure, time-based maintenance, or condition-based maintenance. They all have their place. Should you have any questions or need support from us to make the selections, please reach out to me or to one of my colleagues. And I would like to close this part of the webinar and hand it back over to Savannah if there are any questions that has been submitted. Thank you for your attending this conference.
Thank you, Johan, for your presentation on condition monitoring. We have run out of time for questions. We did get some in, but I will go ahead and close out the webinar. And of course, we are happy to answer any questions that you have. So if you will please just go ahead and enter your questions on the Q&A box at the bottom of your screen, and we will leave the presentation open for a few more minutes to allow you time to do that. And then we will send out answers later. So as mentioned before, this webinar is part of our series of Wednesday webinars about smart maintenance and asset management related topics. Next Wednesday at the same time, we will talk about F1 methodology for efficient turnarounds. More information and registration again via our website, stork.com. This presentation, the recorded webinar, and a related white paper will be available on the Stork website, and you will receive an email in the coming days with the link to all of that information. Thank you again for your attention and your contribution. I hope you have a great day. Stay safe and know that we are your partner in the field of smart maintenance and asset performance improvement. We are here to help you.